Hello class, welcome to this lesson 4.7. We're going to be talking about the multiplication counting principle as well as permutations. So the essential question we want to address is how can we efficiently count the amount of ways that a process can take place using the multiplication counting principle and permutations. So our learning goals are to be able to use the multiplication counting principle to determine the number of ways to complete a process that involves several steps. We're going to talk about using factorials to count the number of permutations of a group of individuals, and we're going to be talking about computing the number of permutations of n individuals taken r at a time. All right, so our vocab includes multiplication counting principle, otherwise known as the fundamental counting principle, permutations, and factorials. All right, so let's first discuss the multiplication counting principle. So the best way to talk about this principle is to offer an example. So suppose there's a restaurant offering the following 3-course menu. So we have appetizer, we have a main dish, and we have a dessert. And you have to order those 3 things. So let's say you wanted to order a 3-course. How many different ways are there to order meals from this particular restaurant? Well, you could start with a list. So if you look at the appetizers, you could start with, say, butternut squash. So we can say the butternut squash soup, followed by the pork chop dish, followed by the chocolate cake. Alternatively, you can get the soup, you can get the pork chop dish, and then you can switch to the tart dessert, and so on and so forth. So you can continue listing all the options and get the total number of meals that way. However, we want to be efficient with this process. So let's look at another option of doing this. Well, we could also try a diagram. So if we look at a diagram, almost like a tree diagram, we have the appetizers listed first: soup, green salad, or Caesar salad. And then for the soups, we could use the pork. We could order the pork, steak, chicken, or salmon. Same thing for the green salad: pork, steak, chicken, salmon. And then when we order the pork, we could order cake or tart for all those options. So that's another way of listing all the options. However, that does take some time because you will have to make the tree diagram, like this, almost like a tree diagram, with all the various options, and that can take some time as well. Notice that if we count all the options here, we have a total of what it seems like, let's see here, total of 24 possible dishes here, or different meals. All right, well, let's use a shortcut though. What's the shortcut for this? Well, notice that there are 3 choices of appetizer, there are 4 choices of main dish, and there are 2 choices of dessert. So we could say, if we talk about appetizer, main dish, and dessert, there are 3 possible options for appetizer, 4 for main dish, and 2 for dessert. So if there are 3 ways of doing something, 4 ways of doing another, and yet 2 ways of doing something else, we can multiply those different ways of ordering those different dishes. And in this case, we get 24 different meals, which follow precisely from the diagram above. This is known as the multiplication counting principle. So let's talk about this in a little more detail. The multiplication counting principle is a process involving multiple steps. So suppose there are k steps. Suppose that there are n1 ways of doing step 1, n sub 2 ways of doing step 2, and so on. The total number of different ways to complete the process is n1 times n2 times n3 dot 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 all the way to nk. So basically you're multiplying all the different ways of doing stuff together. And this is called the multiplication counting principle. In this case, the n1 was the 3 ways of doing the appetizer. The n2 was equal to the 4 ways of ordering dessert, and the n3, or nk in this example, was the 2 ways of ordering dessert. Very simple principle. This is also known as the fundamental counting principle. Because it follows, from a fundamental, um, it's a fundamental theorem, in essence. So we're going to be using this quite a bit in this lesson. So let's look at an example. The standard license plate for California passenger cars has one digit, so in other words, a number, followed by 3 letters, and then 3 more digits. The first digit cannot be a 0. The first and third letters cannot be I, O, or Q. How many possible license plates are there? So again, we're going to use the fundamental counting principle in order to count the total number of license plates rather than doing a diagram or listing them all out. So in this case, it says that there is one digit followed by 3 letters and then 3 more digits, right? So we have one digit, 3 letters, and then 3 more digits. So it says the first and third letters cannot be I, O, or Q. So let's look at the first letter, the first digit. So we could have a digit from 0 through 9. However, it says the first digit cannot be a 0. So therefore, we only have the total number of options here are 1 through 9. So basically, we only got 9 numbers to choose from. 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't choose 0, however. So that would only limit us to 9 possible choices for the first digit. Now for the second digit, well, notice that there's 26 letters in the alphabet. However, the first and the third letters cannot be I, O, or Q. This means we're limited to the rest of the 23 letters in the alphabet. So we have 23 options left in the alphabet. Okay, so we have 23 possible choices. Now it doesn't say that we can't repeat. So we could repeat. So there's a possibility of repetition here. So I could choose another of the same letter. It doesn't say anything otherwise. So in this case, the next option I still have 26 letters left because I could use I, O, or Q. And I can repeat if possible. And then for the third letter, it says it cannot be I, O, or Q. So again, we have 23 possibilities. And then for the fourth digit, it says here followed by 3 letters. So we already did our 3 letters, right? These are our 3 letters. And then now we need 3 more digits. So in this case, the rest of the digits could be 1 through or 0 through 9, right? So it's possible to end in 0 or start in 0. So we could have 10 possible digits here, 10 possible digits here, 10 possible digits there. Now note that if we cannot repeat, this limits the number of license plates we can have. Because now instead of having 10 numbers here, I only have 9 numbers there, and then 8 and 7 and so on. But here we can repeat, so we have plenty of numbers or letters to choose from. So now the fundamental counting principle states that we can multiply these total possibilities together. Remember the n1 times n2 times n3 ... to nk? Well, that's what we're doing here. All right, so in this case, the total number of license plates, if we multiply those numbers together, we get 123,786,000 total plates. And that is a lot of plates. We definitely did not want to make a tree diagram out of this. It would have been an immense tree diagram. And that's why we have the very useful fundamental counting theorem or principle. All right, so now we're going to look at permutations. So the multiplication counting principle helps us determine how many ways there are to arrange a group of objects. So we can use it to count, the number of things, right? We can also use it to help arrange for arrangement purposes. So, for example, suppose we have 5 framed photos of different family members that you want to arrange in a line. how many different ways are there to arrange these photos? So we're talking about arrangements here now. So in this case, let's look at some examples. You could have a photo of your sister, dad, brother, mom, and yourself in that order. Or you could arrange it so that you have a picture of yourself, then your sister, then your brother, then your mom, and then your dad. In this case, these are two different arrangements. And notice that in this case, the order of the objects matters, right? So the order matters here. If in this first arrangement, your sister is first, and the second arrangement, your photo is first. But these are two different arrangements. So notice that there are going to be a lot of options for this in which the order matters. So how do we go about doing this? Well, to determine how many ways to do this, we can count the options moving from left to right in the line of photos. So for example, the number of ways that you can choose photo number 1. So we'll say this is photo 1. In this case, photo 1, you have 5 options of choosing that photo. You can choose any of the 5 photos. Yourself, mom, dad, sister, brother, etc. Once you choose that first photo, now you're stuck with, for the second photo, you're stuck with 4 options. Then for the third photo, you're stuck with 3 options left. Once you choose that, then now you're stuck with 2 options. And lastly, the last photo, you only have the 1 option. So if you think about it this way, it simplifies the problem immensely. 5 and then 4, then 3, then 2, then 1. And then by the fundamental counting principle, we can multiply these ways together. And in this case, we get 5 times 4 times 3 times 2 times 1, which is going to be 120 different ways or arrangements. Very simple. So now arrangement like this in which order matters is called the permutation. So in this example, we have 120 permutations, 120 arrangements in which the order matters. All right, so let's talk about permutation. So the definition of permutation is a distinct arrangement of some group of individuals. In this case, when we mean distinct, we mean, the order matters. All right, now that we know what a permutation is, we're going to talk about another way of calculating permutations. Notice that in order to talk about that other way, we need to talk about what is known as a factorial. So notice that the patterns like 5 times 4 times 3 times 2 times 1, things like this occur so often in counting problems that mathematicians invented a special name and symbol for them. And we call 5 times 4 times 3 times 2 times 1, we call it 5 factorial. It's not pronounced 5 or 4 or 3 with extra emphasis because of the exclamation mark. It's actually pronounced just 5 factorial or 4 factorial or 3 factorial. All right, so then what is this factorial? So for any number n, we define n factorial as n times n minus 1 times n minus 2 dot 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 all the way to 1. So simply we multiply all the numbers starting with n, whatever the number is, and go all the way down to 1. So if we have 6 factorial, well then we have 6 times 5 times 4 times 3 times 2 times 1. If we have 100 factorial, then we go 100 times 99 times 98 all the way down to 1. So you can imagine these numbers are immense. If you have, even if you did 10 factorial, the numbers will be quite large. And there is a function for this on the calculator, which is very useful when you're doing calculations involving factorials. All right, so the manager of a youth baseball team has picked 9 players to start an upcoming playoff game. How many different ways are there for the manager to arrange these 9 players to make up the team's batting order? All right, so you have 9 players and you want to arrange these 9 players. Now notice that the order matters because the order in which you select the players, that's the order in which they start batting. So this means order matters. So if you're the first one selected, then you're going to be the first up for to bat. All right, so because order matters, we're looking at, a permutation. Now, how do we calculate this? Well, quite simply, you have 9 slots for 9 players. So you have player 1, player 2, and so on. So if you're looking at the first option, well, I only got 9 options for that slot. I have 9 players that I can choose from because I haven't chosen any players yet. Once I choose that one player, now I only left with 8 players left, and then 7, and then 6, and so on. Then by the multiplication counting principle, I can multiply these different ways together and get my total answer. Now notice that this is simply 9 factorial, right? So this is 9 factorial, so we can calculate this. So in this case, 9 factorial is actually equal to 362,880. And that's the advantage of the factorial, is that most scientific calculators have a factorial function that you can actually use to calculate this. In this case, we have 362,880 possible batting orders. Quite a bit. And you wouldn't think that there was that many, but if you start listing them out for yourself, let's say you had 9 names on a roster, and you wanted to pick 9 of them and put all the different orders, you'll see for yourself that there's a lot of possibilities here, which is why we have these methods of counting so that we can shortcut it. All right, so far we've shown how to count the number of distinct arrangements of all the individuals in a group of objects. Now, sometimes we only want to count the number of ways to select and arrange some of the individuals in a group, not all of them. So how do we go about doing that? So let's look at an example. Say Mr. Soto would like to get the students in class involved in some sort of action in class. He puts names of all 28 students in a hat and mixes them up. He then draws out 3 names one at a time. The student whose name is picked first gets to operate the display calculator. The second student is in charge of reading answers to homework problems, and the third student writes class notes on the whiteboard. How many different ways can Mr. Soto fill these 3 jobs? Now notice that the order matters here. Why? Well, because the first student gets a certain task, the second student picked gets a certain task, and the third student picked gets a different task. So the order in which I pick the students matters. So keep that in mind. So we're looking at permutations. Now, we have only 3 slots here for 3 names. So for student 1, or let's say that the first one is job 1, this one's going to be job 2, and then this one's job 3. Well, for the first job, I only got 28 choices for that student. 28 students that I can choose from the hat for the first job. Once I choose that student, I only got 27 students left for the next job, and then 26 students left. And that's all you got to do. So you don't have to do all of them. You just have to do those 3, because we're only looking at 3 jobs. In this case, we multiply those 3 numbers together. We get 19,656. And we'll just call this permutations. All right, so now we're going to look at another way of calculating permutations. So we used the fundamental counting principle to calculate permutations, but now let's look at an alternative way. So this is the symbol for permutation. So if we wanted to do permutation, the symbol would be this guy right here. And this is read as the permutation of n objects taken r at a time. So in the case of P 3, 2, this is read as the permutation of 3 objects taken 2 at a time, for example. So instead of using the multiplication counting principle, we can use the following formula. So this uses factorials. Surprise, surprise, because we already mentioned factorials, and we were going to use them exactly for this purpose. So the permutation of n objects taken r at a time is n factorial divided by n minus r factorial. So remember that 4 factorial is 4 times 3 times 2 times 1, dot, dot, dot. And 0 factorial, interestingly enough, is always equal to 1. So 0 factorial is always 1. It's not 0. And 1 factorial is also equal to 1. Interestingly enough. All right, so the importance of using this formula is that most scientific calculators have a permutation function in the scientific calculator itself. So if you can write it as a permutation, then it simplifies the calculation immensely because you can just plug away at the formula in the calculator. All right, so a youth baseball team has 15 players. How many different ways are there for the team's manager to select and arrange 9 of these players to make up the team's batting order? And then part B is how many different ways are there for the team's manager to select and arrange the whole team for batting order? So let's look at part A. So we're looking at 15 players and we're looking at 9 of them. And the order matters. So that means we're looking at a permutation. So let's do method 1. Method 1 is the fundamental counting principle or the multiplication counting principle. In this case, you have 9 slots. So we have 15 choices for the first slot, then 14, then 13, then 12, 11, then 10, 9, 8, and then 7. And then by the fundamental counting principle, we can multiply those together to get our total number of possible batting orders. In this case, you get 1,816,204. I'm sorry, 1,816,214,400 possible batting orders. All right, so method 2, we want to use the permutation. So in this case, we want the permutation of 15 players taken 9 at a time. So using the same idea, 15 players, you're choosing 9 of them. So in this case, we have 15 factorial over 15 minus 9 factorial. Now I'm doing this because I want to show you how to calculate these permutations using the formula. So we have 15 factorial over 15 minus 9 is 7. So this is going to be 7 factorial. Actually, it's not 7. It is 6 factorial. Bad math there. So 6 factorial. Now 15 factorial is 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 factorial. Why do I stop at 6 factorial? The reason I stop at 6 factorial is I know that 6 factorial is 6 times 5 times 4 times 3. So what I can do is, since I got a 6 factorial on the bottom here, I can cancel it out, right? I don't have to write the 6 times 5 times 4 times 3 because it's going to be the same on the bottom. So these cancel out. And lo and behold, if you look at the answer that we have here, it matches the fundamental counting principle or the multiplication counting principle, which is amazing indeed. So in this case, we're going to get the same exact answer. So if you just plug this on the calculator, which I'll show you how to do that in class, you'll get 1 million, you'll get the same number because it's the same exact calculation. All right, so part B, how many different ways are there for the team's manager to select and arrange the whole team for batting order? So in this case, we have 15 times 14 times 13 times 12, and so on, right? So in this case, let's do the permutations. So if we look at the permutations, we have 15 players taken 15 at a time because we want to arrange the entire team, right? So in this case, we get 15 factorial over 15 minus 15 factorial, which is 15 factorial over 0 factorial. Well, 15 factorial is just 15 factorial. Remember that 0 factorial is just 1. So anything divided by 1 is itself. So this is just 15 factorial. And if you use the fundamental counting principle, you would be using the same thing. 15 times 14 times 13 times 12 all the way to 1. So this is the exact same calculation. So in this case, 15 factorial. So we're going to go ahead and calculate that now. So in this case, we have 1,307,674,368,000 possible batting orders. And that's just for 15 players. That's insane. You can now see the power of the fundamental counting principle and of permutations. We can use this for counting otherwise seemingly impossible tasks, like for example the lottery or anything like that involves an enormous amount of possibilities, and then we can calculate the probability of that happening. So very important in those applications. Alright guys, this is going to be it for the lesson. So the next lesson we'll be talking about combinations and probability. So we're going to be applying the idea of combinations and then actually do probability using the counting methods. I'll see you guys in the next video.